I'm from Japan. So, this is a joint work with Kosuke Nakago and Mikhail Hanifusek. They are now not from with us, but Shoji Nakayama is sitting over there. So we have a lot of talk for this conference in the workshop, learning about how to more abstract representation operation, but I will try the simplest one of the circuit model. Of course, some unitary operation can be decomposed into the pieces of gates in the circuit model. And in this circuit model, we have like to represent unitary operation on n qubit, we use very smallest amount of qubits, 3 qubit, and then 3 wire, and then any unitary can be decomposed into the elementary gates. And of course, the circuit should be written from left to right, and there's no loop is allowed, or proper temporal ordering should be satisfied. But of course, quantum mechanics is not this strict disposal structure, as long as total amount is completely positive. So if a circuit is a causal not following the circuit rule, how to understand the implemented gate? That's maybe an interesting question. And there are several interesting a-causal operation has been investigated. For example, this closed time-like curves and how to understand this in quantum circuit. There's some way this understanding is CPC in terms of post-selection, or this kind of funny controlling from your future, or like this funny gate can be considered once appear in this measurement-based computation. So of course you can consider that kind of circuit, but that cannot be unitary. Another thing of the a-causal operation is like the Jurio as presented as a quantum switch implementation of some two sequence of unitary controlled by the control gate. Sorry, this is 1, 1, first. And we wanted to implement this gate by performing 2 gates G and F at the same time. So they are not causally order, and then putting some of the general operation before and after, and this kind of quantum calm idea. The Jurio have been shown this cannot be done in quantum circuit. So we think other model, the other models of quantum computation, and we wanted to consider some consequence of a sequential gate to be performed parallel. And we consider adiabatic computation may be a good model for considering parallelization. So, not a usual adiabatic computation, but there is an adiabatic gate teleportation. That is recently, not so recently, but some time ago it was presented. So this is adiabatic computation in general, starting from ground state of some Hamiltonian and gradually changing the Hamiltonian. You want to drag your state to the answer of your computational problem. And in this case, this teleportation can be applied in this adiabatic manner if we use 3-qubit system. And this adiabatic gate teleportation actually implements input, the output is unitary operation performed the input by, you apply unitary, this is like a gate teleportation. Anyway, right. And the nice thing of adiabatic gate teleportation is it can be a model of post-selection, gate teleportation with post-selection. So it's a-causal. The post-selection is one of the a-causal, model for a-causal quantum circuit, a quantum gate. And it's like something familiar with, start with bell pair, you apply this some unitary in one hand, and then we could plug some input state we choose. And if we are lucky to perform one of the Bell measurements, we can always, the final state is the state applied by u. And this only happens, of course, it's post-selection, so only happens probabilistically, and then only one quarter probabilistically. But this adiabatic gate teleportation scheme can simulate the same process by using adiabatic unitary operation. Of course, it's called teleportation, but it's not teleportation at all. It uses global unitary operation, time-dependent Hamiltonian, to do the same thing. But input is going this, and output is going this. And so, nice thing is we can deterministically drag input state to arbitrary unitary state. If we have a resource where this bell pair with the unitary operation is prepared, and some Hamiltonian which they coordinate that operation. So, as I said again, this adiabatic teleportation simulates one aspect of gate teleportation with post-selection. However, there are very nice another property of gate teleportation. This is gate teleportation can be actually used to parallelizing sequence of gate. So, for example, like you could concatenate this gate teleportation, and if you're lucky, so we both have an outcome like Bell state, we can like push these two together, and then so sequence of gate U1 and U2 can be performed by parallelizing U1 and U2 are performed at the same time, long time before, and if you have a nice measurement outcome. So instead of operating U1 and U2 in order, this temporal order of U1 and U2 are disappearing in parallelizing rotation. So we wanted to, like it sounds too nice, it's every sequence operation can be done parallel by using the power of large Hilbert space. And that's too good to do, of course. And of course it doesn't work like that. So, but if you use the similar thing, concatenating or this like put together this adiabatic gate teleportation scheme, actually it doesn't give you the sequence of operation. So usual Hamiltonian system to which realize one gate cannot done by like putting together at the same time. However, interesting thing is if we use this Hamiltonian, so previous gate teleportation Hamiltonian is made of X and Z, but we have a Y like an identity, which is so previous one has the interaction is only somehow like X times X and Z times Z, so it's a stabilizer, inside stabilizer. And but if you add extra interaction term, in physics this is called correspond to Heisenberg Hamiltonian with some shift of ground-state energy. Actually, this would allow this adiabatic gate teleportation to be parallel somehow. And this is this Hamiltonian is something like you have two spin Heisenberg interaction, but the second spin have a particularly twisted, depending on the operation you want to apply. So in this case, there's no problem. We can do this like parallelized gate teleportation, which is in real life is only happening. It's probabilistic. Can be simulated in this parallelized manner. Right. So the nice thing of here is this, in this method of realization of the sequence of unitary gate into the parallelized there, all the Hamiltonian here is divided, which Hamiltonian use, so which unitary operation we want to implement is encoded all in the initial Hamiltonian, and which way to operate is encoded in this, like which qubit is interacting with which qubit. So time is not, here the adiabatic quantum computation have a time parameter, but it does not, here in the time, does not depend on the order of what we want to apply. So nice things here is all the temporal order we want to apply for the operation is encoded in all the spatial order of an interaction. So we can consider different order of unitary. So the previous one is U1, U2, but U2, U1, U2 first, U1 first can be done in a similar way, but slightly changing the spatial order of the final Hamiltonian. And that means by slightly changing order of spatial, just spatial order Hamiltonian, we can control the temporal order actually act on the qubit. So that would allow, so in time basis we cannot change, once we set up the time ordering we cannot do anything more, but here in this, parallel gate teleportation scheme, we can consider a superposition, sort of like Hamiltonian like this. Depending on the control qubit, you apply this Hamiltonian here, and this one is Hamiltonian. So it's kind of control unitary operation. In that case, we can perform, so instead of like a U1 and U2 unitary operation are applied at the same time, but one spike of adiabatic evolution would make this quantum switch to be implementable. Okay, so, but of course, if every sequential operation can be done parallelized, it's too nice to and then the problem is like adiabatic evolution have to be going slower and slower and slower when you parallelize. So what is the point? Like it's no speed up by parallelizing, but the important thing is we don't have a ordering, the temporal ordering encoded in the time in this scheme, but everything is somehow spatial. Ordering is temporal ordering is chosen by the spatial mode, and then this spatial degree of freedom, we have more way to play compared to the temporal degree. Okay, so we haven't proven quadratic speed up, the slowdown is like it could be there might be some way to make it faster maybe, but it cannot be faster than this quadratic reciprocal. Mm-hmm. Right. Right. Okay, I see. Yeah, that's right. Yeah. So, So what do we want? We want to parallelize, but we cannot make it faster. And what is the good use of this is not so. So I don't think it's useful for speed up, but it may be useful for simulating some proposal gate operation, or implementing some kind of, like a quantum home in terms of like temporal, so like a temporal parallelizing way. So there's a one way. Anyway, so it's time, so I just summarized that we consider parallelized version of an adiabatic gate teleportation. And here it's very important that Hamiltonian can distort, like it's basically a maximal entangled state, and with some twisted Hamiltonian. And we usually never look at this kind of very funny looking Hamiltonian. But this Hamiltonian originates have a very strong power to parallelize, although it's not useful for speed up. And actually, the nice thing here is this Hamiltonian, actually, using this Hamiltonian, we can perform transpose of unitary operation, just performing U. And creating U from U transpose is quite a non-trivial task. And this transpose them in coming out the free is a good property related to our time reversible symmetry, and it's sort of interesting to analyze why this Heisenberg Hamiltonian is useful. Okay, let's time this pretty quickly. And then time for one question. Who would like to ask a question? If networks are acausal, why would sequential order matter? This is very nice question. I don't quite understand that. Could you complain a couple of times that if you have parallelize everything, but you should consider acausal? Why would sequential order matter?
Right, if it's doesn't matter in that case, but it's have a power to parallelize. So it's a simulation of a causal, and this parallelize is different thing. Two different things, but same. Yeah, it's two different things, but the same mechanism, same system can come